Welcome to the Global Composites Experts webinar series. My name is Wenbi Yu, Director of the Composite Design Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in this beautiful Indiana Manufacturing Institute. All of you are welcome to visit us when life returns to normal and it is safe for us to travel. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, SciTech Survey, MAC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. Next, I will show a brief commercial from one of our sponsors.
In case you are wondering, you are not fighting molding defects alone. Introducing Modex 3D, your plastic injection solution. With powerful molding simulation features, friendly and easy-to-use interface, Modex 3D pinpoints design problems before production and achieve better product quality with less time, less cost, and less waste. Modex 3D, the best partner for plastic industries.
Thanks again for our sponsors' support. We invite more organizations to join them to serve the global composite community together. This webinar will be recorded and made available on CDM Hub. An email will be sent to you once the recorded video is available online. The presentation will last about 40 minutes and will have about 15 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the speaker's presentation, your questions will be read and answered. Next, I will ask Dr. Pipes to introduce our distinguished speaker today.
Welcome, colleagues. Those of you who work with us all in the field of composite materials, we're delighted that you're here with us today to hear this wonderful lecture from Professor Suresh Advani. Professor Advani holds the George W. Laird Professorship in the Mechanical Engineering Department at the University of Delaware. There he also serves as the Associate Director of the Center for Composite Materials, an organization for which I have lots of fond memories, as you might know. Suresh Advani also is a recipient of many important awards. Not only is he an outstanding Google Scholar with a rating that's perhaps better than any I've seen to date in our composites field, but he also received the Outstanding Research Award from the American Society of Composites in 2015, the Composite Educator of the Year Award in 2015 from the Society of Plastics Engineers, the Outstanding Doctoral Graduate Student Advisory and Mentoring Award in 2008, and he, of course, was named into his named professorship in 2006. He holds his PhD from the University of Illinois at Urbana-Champaign, where he worked with Professor Chuck Tucker, another extraordinary colleague in the field of composite materials, one who I value very much. Professor Advani, as you know, began his career at the University of Delaware as an assistant professor in 1987. At that time, I happened to be at the institution, and he and I worked together for several years. I must say he taught me much about infusion of composites with his wonderful new LEMS program that he now his computer software program is promoting across the world to help us understand these important problems. Today, you'll hear more about this. I'm very much looking forward to hearing his presentation today, and I'm delighted to welcome him here to Purdue University Composites Expert Seminar Series. Dr. Advani.
Thank you, Byron. It's a great pleasure to be invited to the Composite Manufacturing and Simulation Center, as that's what I do, and I've been doing it for the last 30 years. One other thing to add is Byron was the one who hired me, took a chance with me at Delaware, and hopefully I haven't disappointed him. So over the last 3 decades, I've been working in simulations of liquid composite molding, and I'll talk about what I've been doing. And but before that, just wanted to show you that the Composite Center started in 1974 at Delaware. I think it was the first composite center. And then in 1978, Professor Pipes became the director and helped us win the NSF Center for Excellence ERC, the first ERC ever. And after that, the center had never looked back with that momentum. It continues to grow and continue to be recognized as Center of Excellence by various agencies. Also, the other thing that is going to happen, I want to tell you about, is that the next ICCM will be held in USA. It's the International Conference on Composite Materials. It will be in Baltimore, and in 2023. As you know, Baltimore is very close to Delaware, only 60 miles, and we were not big enough to have such a big conference. And one of the reasons also we wanted to do this is because it's going to be the 50th anniversary of the center. So, of course, before I start my talk, I want to really recognize all the real stars over the years, my graduate students and postdocs who have really contributed to everything that I'm going to be talking about today. So if it wasn't for them, we wouldn't have much to talk about. So today, my goal is to give you a takeaway message. Is to demonstrate to you that process models and simulation do contribute to advancing and making manufacturing efficient. And today they're quite powerful tools and ready for you to use them and build on them to address the current manufacturing challenges in liquid composite molding. So this is going to be my takeaway message. So first, for those of you who are not familiar with liquid composite molding, it's a family of processes where you have a dry fabric and you are injecting the resin into it, either in using some sort of pressure or force. So the most common one that you'll be familiar with is resin transfer molding, where you have two rigid tools and you compress your fabric while you inject it under high pressure, the resin into the mold. Now, of course, you couldn't make a wind blade like that because the mold will be huge. So vacuum assisted resin transfer molding allows you to make large parts by, instead of pushing the resin in, it pulls the resin in with just 1 atmospheric pressure. So you don't need a rigid top to keep the pressure in. And so that's the Wharton process. And usually, because you only have 1 atmospheric pressure, you use a distribution media that will allow you to basically get the resin to flow in various corners of the mold. And I'll talk a little bit more about it. Then RTM light is a variation. It's kind of in between the two, where you put in a compliant tool on top, which will allow you to normalize the pressure. And compression RTM is the one that is more important here, because what it does is it reduces the cycle time. So instead of having a distribution media, it has a gap. You can inject the resin in the gap, and then you close the mold, and then you push the resin into the dry fabric. So that's the different or some of the processes, and you can make very complicated parts with it, which apply to aerospace, automotive, sports industries, and you can make very, very large parts with that. So, as I said, the RTM and VARTM are the two main processes I'll talk about. So, I'll give a little more introduction here. So, you take the fabric, you place it on a tool, then you close the mold with the rigid tool, then you inject the resin until it reaches the vents, and then you keep the mold closed until the part cures, and then you demold the part. In Vartam, you have basically the same thing where you have a rigid tool on which you lay the fabric, and then you have a peel ply. Everything about the peel ply you discard. And so after that, you have a distribution media that allows the resin to flow faster in the in plane direction. So all it has to go is through the thickness direction. So this allows it to kind of flood the top surface, which is helpful. And then you put a vacuum bag on top of it. You apply the vacuum to compress the preform to get the fiber volume fraction. And then after you do that, you open the resin, which is at atmospheric pressure, and the resin will then start to fill the mold and go towards the vent, and you keep the vacuum on until the part cures, and then you demold it. Okay, so what are the issues in this process? This issue of, can I saturate all the fibers, all the regions in between the fibers? Otherwise, I'm going to have a lot of voids. Where should I locate my injection and vent locations? How much time will it take me to develop a prototype? And how do I reduce the cycle time, and can I introduce process control? And the biggest issue is reliability and repeatability. Can I repeat this part? So there are many challenges, and one can address these by integrating flow modeling in prototype design, accounting for material and process variability, dimensional tolerances, and then introducing process control and automation so that we can manufacture large and complex parts. So hopefully I'll show you some of the examples today that will convince you that we are very close to be able to take simulations and be able to address all these challenges. So, in mold filling, why do we need a simulation? The reason we need a simulation is because when you close the mold, you cannot see anything inside. So once you wait for the resin to come out of the vent and you open the part, you may end up getting voids in the part, and then you have to throw away the part because the part is already cured. So simulation allows you to see inside and design resin injection processes to optimize the filling time, minimize void, reduce the development time, integrate the process with the mold design, and address the material and process variability by passive control to improve yield, or have active control and automation. So I'll show you examples of those. So my second thing is to talk about the science behind this modeling and simulation, and maybe more about the features of what it can do. So as you can see that there are, you can have micro scale or macro scale voids in this, because you can end up getting voids inside the fiber toes, or have dry spots like this, which you can see by the naked eye. And sometimes you have this micro voids, which you have to go under the microscope to see. So this is the issue that we want to address. So we'll do that at 3 levels. So at the macro scale modeling, where we can predict the dry spots and the voids, and how we can use design and optimization and control. And then we can go a level below and couple the two. So the level below is that you have fiber toes, and then you have region in between the fibers. So you can look at how you're saturating the toes along with creating the dry spot. So these two are connected. So we can look at dual scale flows. And then finally, at the micro scale level, within the fiber toes, you can get voids because of how the resin spreads, what is the capillary effect, and so forth. So the idea is that you can address all of these 3 issues through simulation. So first we look at the macro flow. At the macro flow level, we model the flow as Darcy's flow through porous media. And basically you inject the resin at some point, and as the resin moves, it follows the Darcy's law, which is the average velocity is proportional to the permeability of the fabric and to the pressure gradient. And then you combine this with the mass conservation to get a governing equation in terms of pressure. Okay, with the boundary conditions, which is at the inlet, you can have a constant injection pressure or pressure changing with time, or you can have a flow rate changing with time or a constant flow rate. So you can do all of that. And then if you have no flow out of the mold walls, you can apply that boundary condition as well, that the velocity or the pressure gradient is zero. And at the vent, you can either have vacuum pressure or you can have some atmospheric pressure if you're doing RTM or injecting under high pressure. Now, of course, when you do this, one of the things that happens is the flow front moves. So you have to address the movement of the flow front in your simulation. Now, the other thing you do need to do is characterize the permeability of the fabric that you're going to use, which turned out to be a major impediment in order for people to use the simulation, because having this data is very crucial. And obviously, you also need to know the viscosity of the resin. And you can do this in Wharton, where you have 3D flow, because the flow is also going through the thickness and as you're flooding the top surface. So now here you have more permeability values to find. So the permeability in the X direction, Y direction, Z direction, and if the fabric is not aligned in the flow direction, you also have these cross permeabilities to find. So the way we do it is we don't remesh the problem. So you create the mesh and then you associate a fill factor with every node. And when the fill factor is zero, that means there is no resin there. If the fill factor is one, that means it's filled with resin. And when the fill factor is between 0 and 1, then you know that that you have that node is on the flow front. So we use that idea and avoid the problem of remeshing. And obviously, we need to know the permeabilities of the elements. So you can actually have element-wise permeability, so they can change in each element. So, of course, to measure the permeability, there is all kinds of right now measurement benchmarks going on, because this is a problem that gives you, every time you do an experiment, you get a different answer. So you have to come up with a very good way of doing this. And we have a few of these techniques that we have come up with, where we look at the top and the bottom, and then we use that to kind of measure the permeability in the Kx, Ky, and Kz direction. All I want you to notice here is that usually the KZZ, the through thickness permeability, is much, much lower than the Kx and Ky, up to 2 to 3 orders of magnitude lower. And this in Wharton could be an issue. And then, of course, as you lay the fabric, the fiber direction changes and the fiber volume fraction changes. So you have to couple this with a draped, when you drape this, as you can see here in the experiment, as I shear the fabric, the direction of the flow has changed, and also the fiber volume fraction has changed. So one needs to be able to not only measure the permeability in the mold, but then have a way to take something like this and then drape it and get the fiber volume fraction of the draped fabric, and then convert that into permeability values and before solving the flow problem. So one of the things we've been recently doing with one of my collaborations in France is that we're using a paper to look at the pressure that is applied on the fiber toes. And then from that, we can actually configure what we can reconstruct how the fabric looks like uh, inside the mold when it is closed. And this will allow you to actually get a much more accurate permeability value. And so once you have the permeability values, you have the mold, designed, so you can use that any kind of software to create this GMesh or any CAD profile. And then if you need to drape the fabric, you'll have some way to convert that. You input that into the simulation model, and the simulation allows you to find flow fronts, the pressures, temperatures, and also the saturation of the toes. It's a nice research tool, because you can actually write sub code that will allow you to introduce control, It will also allow you to change the filling procedures and so forth. So that's the one of the big advantages. And over the years, we have validated the simulation with all kinds of experiments that we've done. This is like a 4 foot by 3 foot window frame, and you can see on the left is your experiment, on your right is the simulation. Here are some more examples of the filling, showing you how the simulation and the experiments work well. And here is a 3D part with ply drop-offs and ribs, and we were able to even predict, a dry spot that happened in this part that we were able to predict by applying those same conditions. And it can do any complex 2D and 3D parts without any problem. Uh, Many years ago we were able to do that. The other thing I was talking about is that you can actually write a small script file which will allow you to do things inside the simulation. For example, here, if you're trying to find the best gate location, you can write a small script and keep changing the gate location and finding the fill time. And it can do this all in the background for you to tell you which is the best gate you want to use. Now, of course, you don't want to do this in a brute force way. You want to use some sort of techniques to allow you to be able to find the best location to fill for the least amount of fill time. So if you have a part like this with 3,000 plus nodes, you can, instead of running the simulation 3,000 times, you can use some techniques such as branch and bound search, where you break the mold into different sections, and you keep moving towards the one that's giving you the lowest fill time, and that way you can end up with the actual region which has the gate that will give you the minimum fill time. So you can see here the branch and bound method only took 57 simulations, as compared to, if you were to do this by brute force, it will be 3,037. And if you use genetic algorithms, it takes about 140 or so simulations, and it doesn't give you the most close enough, but not the exact gate location. Whereas the branch and bound method gave you the location that you get from the 3,000 simulation. So this is showing you how you can use optimization with it. So now going to the next level, which is the mesoscale modeling. How do we model flow inside the fiber toes? So what we do is, if you can look at this mold here, I don't know if you can see it clearly, but it's much darker here compared to here because the fiber toes here are not completely filled yet. And the reason is you have, bigger gaps between the fiber toes. So the fiber toe permeability is lower than the regions in between. So, if you don't use the dual scale, then LIMS does this, which is basically it assumes that the toes and the region in between the toes fill at the same time. But if you turn on the dual scale feature, then it will actually tell you how these toes are getting saturated while the mold is, while the resin is moving into the mold. And as you can see, these are all dual scale fabrics. And so what we do in the simulation is for the 2D or 3D elements of the mesh, we attach one-dimensional elements that represent the fiber toes. And so they have their own permeability and their own volume to fill. And so we can do that. But now, of course, we need not only the permeability of the bulk that you measure from the experiment, but you also need the permeability of the toe. So you need two parameters. And then let's say you inject from here, and as the resin is filling the mold, the red area is where all the toes are filled. And between the two black lines is where you have partial saturation of the toes, as seen here. And then obviously, when this front reaches the vent, you might think the mold is filled, but you still may have some unsaturated toes. So what you have to do is you have to leave the vent open so that the resin bleeds through it until this red area, this red front, reaches the other end, which will ensure that all your toes are filled. So it can give you that sort of information if you know your toe permeability. And then you will say, okay, now that means I have to measure two values. And then so we came up with the analytical method to measure both the values from one experiment. So what you do is you inject the resin at one end at a constant flow rate, and the pressure profile will be linear with time at the inlet if it is a single scale fabric. If it's a dual scale fabric, then you'll see that the pressure profile is actually a drooping pressure profile because the toes are filling at a different rate. So now what we do is experimentally we measure this profile, and then we have a analytical expression for how the inlet pressure changes with time as a function of the toe permeability and the bulk permeability. So we try to match that by changing these two values. And by changing these two values, we can match the inlet profile and get both the values from the same experiment. It's not as harder as it seems because usually the slope at the inlet is more representative of the bulk value. So from this slope, we can get the bulk value, and then you just have to play around with the toe value till you can match the pressure profile. And then you can do simulations of like a hood um, and a car hood where you can see how the you have the partially saturated zone and for how long you have to bleed that so that you're able to fill it completely with the dual scale. And then finally, the third scale that I'm looking at is the micro scale of what happens because of the capillary effects, and how does the capillary play a role in here, and what about the contact angle that the resin has with the fibers. So you can actually measure the contact angle on top of the fibers, and usually as you change the contact angle, you'll see that the average capillary pressure changes. So we were able to simulate that and come up with an average capillary pressure depending upon the distance between them and the contact angle. And then we show here that how the average capillary pressure changes with fiber radius and with the capillary angle. And also, as you move one fiber closer to another fiber, you notice that the capillary pressure will also change. So basically, as the fibers move closer, it is higher, and as you move it away, it is lower. So you can even address those things. And the big utility of this is if you don't account for capillary pressure and you're trying to look at a filling time of one-dimensional mold without the capillary pressure, you'll find that the time is the blue curve here because we are not using the capillary flows to fill it faster. But if you account for the capillary pressure, you can see that the filling time drops quite quickly, and that makes sense. And this is very important only when you are close to the flow front where the pressure gradient is not very large, and that's when the capillary pressure comes into picture. And here, what I'm showing you is that we have a way in limbs to attach elements where we can assign capillary pressure, and then we can look at the effect of capillary pressure as compared to the injection pressure. So on the top, when you're looking at the toe saturation where no capillary pressure is applied, you can see that basically you have much larger region that is empty, whereas when you account for the capillary pressure, yeah, a much more bigger region is filled. So the difference is not that huge, but still it can be accounted for. Okay, so that was about the simulation. Now, how do we account for material and process variability in the simulation? So what happens in these processes is that when you lay the fabric, there are gaps, there are channels, and the problem with that is that the resin will go faster along the channels, and so the resin the permeability is much higher, and we call that race tracking. And that race tracking is present everywhere. There's nothing we can do to prevent it, and you can see that how the race tracking will make the flow go faster along the edge, and that can mess up your part, because let's say you put in a vent here after you did the simulation with no race tracking. The vent should be here, the last area to fill, but because of race tracking, what happened was, because the resin went on the top and the bottom, it arrived at the vent sooner than it was supposed to. And then even if you let the resin bleed, you cannot completely get rid of this void. So accounting for race tracking becomes important. And as you can see around the corner here, that you have race tracking. And as you can see in the simulation on the left, I'm saying there is no race tracking along these wheel wells. I've done a very good job of putting the fabric there. And you can notice that because there is no race tracking along those edges, the last areas to fill are these green spots where I will place my vents. And the resin really goes very nicely along these edges. And then if I have race tracking and I can't prevent the race tracking, what happens is along those black lines, the resin will go faster. And then as it goes faster there, what's going to happen is going to arrive at the vents sooner than it's supposed to. And even if you allow the resin to bleed, what's going to happen is you're going to get these regions that will not fill at the end because the resin has already arrived at the vent. So race tracking is an issue, and we need to address that. And as you can see here, this is a 40-foot keel beam that was made by RTM, where the race tracking was not accounted for. And after the fact, I put in the race tracking, and I was able to predict where the voids were at the bottom, which is what they were getting because they uh, had run the simulation without using the race tracking. So I wanted to know, okay, so what do I do with race tracking? How do I know how much race tracking is taking place? Can I kind of control it? Can I measure it? So I had, five students actually do the same experiment, an L-shaped insert where they put the fabric. So you will have race tracking along 5 regions. Okay, so that's along this region, top and bottom. And so what we did was each student did 10 experiments. And this is edge 1, 2, 3, 4, 5. And these are the students. One of them used a laser cutter to cut the fabric. But you can see that this is the average of 10 experiments. And it's not repeatable at any edge. I mean, it depends on how people cut it, how they place it. And that's what creates the variability. So how can we use the simulation where we can account for this variability and improve our chance of success? So let's say first, let's do a passive control when you have a distribution media. So you can put the distribution media that covers the total top of this mold, okay? Or you can use simulation to plan the methodology. So here is an example where I have this A-frame, and I'm going to put the distribution media on top and just cut the distribution media around the A-frame because I don't want to put on top of it. So this is what they will normally do. They'll just cut the A-frame, and then I'm going to make a slight change in my design where I'm going to actually let this distribution media be cut all the way to the end here. I'm going to inject from this end, and my vent is going to be the other diagonally opposite end. So here is the case where you cut it around the A-frame, and now you're filling this. And as you fill this, when the resin arrives at the vent, which is this end, you'll see that you won't be able to fill this area. Even if you let it bleed, there will be some region that will be empty. Now, if you look at just the slight change in the distribution media, and just making that slight change is the thin line between your success and failure. So there are many simple things you can do when you are manufacturing with the composites. Now, we have also done case studies where we allow for race tracking. So we say, what is the best distribution media when you are also having race tracking? I don't have that slide here as I had a limited time to talk. So, but we can do that. And here is the case where what you do is, if you're going to have race tracking either weak or strong, you run simulation for no race tracking, where you are introducing the flow on the left and the right. So you're coming in from the left and you're coming in from the right, and you're filling it. And you can have different cases: no race tracking, or you can have weak race tracking on the top, strong race tracking at the bottom, weak, no race tracking, strong races. You can do all those permutation, and you can see the flow fronts look very different for all of them. So how do you design gate and vent locations in the present of race tracking? So what we did was we said, okay, let's identify the edges where the race tracking will occur. Then we also assign a probability. Like, is it most of the time there will be no race tracking? Some of the time there will be high race tracking. And so you have that probability associated with it, which can actually come from manufacturing data as they're making it. And here's where AI and all those things can also come in handy. And so what you do is you basically have a gate and you have these three race tracking edges that have different probabilities. So we divide that into 4 scenarios along these 3 edges. So you have 256 scenarios for cube, and then you run 256 simulations because our simulations take only about 1 or 2 minutes to run. And you find out which are the last areas to fill, and then you superimpose them, all the scenarios, with the probability. So you, with the probability, weighted probability, and then you find out where will be the resin to arrive at the end. So that's the highest probability is these blue areas. So you'll place your vents over there, and or the yellow area, sorry, not the blue area. That's where you'll place your vents, and just improve based on terms of using this. So here's an example where you have 2 window frames. You could have race tracking along the window frames, and then you have the same probability of race tracking. So you have 5 edges where there's race tracking. So it's 4 times to the power of 5. We run it 1024 times. And if you just did it normally here, you would put, by intuitive design, you'll say, okay, put a vent here, here, and here. Now, if I had the 3 vents and I ran it through the probability and race tracking scenario, my vents come out to be at these 3 locations, which is very different from here and not very intuitive. And now I succeed about 69% of the time because I just run simulations, 1,000 simulations, not telling them where the race tracking is going to take place, and see when it gets completely filled. So I've doubled my, I've doubled my success rate here. Now, of course, it's passive control because I can't get 100% by doing this. So what can you do to get 100% yield is active control, which actually lends itself to automation. So what you do in active control is you need sensors in your mold. So you fix mold geometry, you find out what are all the possible disturbances that can take place, you run the simulations, you optimize where you're going to put the sensor locations that will allow you to identify the disturbance. Then you decide what control action can you take to make sure that your mold will fill due to the disturbance as well. So there are many types of sensors available that can lie flush with the mold: point sensor, lineal sensors. There are also textile sensors. And so here's an example that we did on the ONR program where you have a weak race tracking or a strong race tracking, depending upon how well the edge is fitted here. And there are 5 regions. So along this insert and top and the bottom. So you have 32 cases, either with weak or strong, and so it will be 2 to the power of 5. And then what you do is you run all the 32 cases, and then you figure out where can I put the sensors. So very early on in the process, I'm able to detect which of the 32 scenarios or which of the scenarios closest to the 32 scenarios is taking place. And then I have a customized control action. I have introduced 2 auxiliary gates that I can open with different pressures so that I can always drive the resin towards the vent, which is this green hole. So I do this beforehand running the simulations. I put the sensors in the location. I create the control database. As soon as I know which scenario is taking place, the control database tells me what action I need to take. So now the molder, all they have to do is just put the fabric in, and they don't have to worry which of the 32 scenarios is taking place. The lab view automatically takes care of that. So here you can see on the top, that if you did not use any control, scenario 29 took place in one of those where the resin was going faster here, and the resin reaches a vent and you have a dry spot. Now, what we did was we did this experiment 15 times, and we didn't know which scenario was taking place. And in most of the cases, it filled. And in one case where it didn't fill was because of the sensors failed. It wasn't the simulation failed. It was the sensors that failed. So it told us you need to have more redundancy in the system. So here is the experiment on the left and simulation on the right for when you actually allow flow control. So you can see that the resin is moving faster here. You can look at the experiment, and here is the auxiliary gate, and that gate will open and push the resin towards the vent, which is over here. And you can see that that way you will be able to fill the part by pushing the resin towards the vent. So this also lends itself to automation. So you can account for the variability that happens inside the composites by using sensors and then having some control schemes to design them. Yeah. So, but how to do this in Vartam? In RTM, it's easy because you can push the resin with the pressure. So in Vartam, we came up with this idea where what you can do is, because the entire mold is under vacuum, I can use a little chamber to release part of the vacuum. By releasing part of the vacuum, I can increase the permeability locally. And when I take away this chamber, it will compress to the same fiber volume fraction. But by having this there, I'm attracting the resin to come over here because there is less resistance. So we build this setup with gantries and with the robotic arm that would do that on top of the mold, and we had that chamber, and also we had a camera on top that told us where the resin needs to go, and then this information was actually put in a control loop in the controller of the lab view. But here the difference was we did this online. So in the lab view, we could look at where the flow front was. We take that image, we send it to LIMS. LIMS now starts from here. It will run a few steps to see what is the best course of action, or where does the chamber need to go, so that you are able to fill this without creating a void. And so this was all done online. And here is I'm going to show you one of the experiment where there was race tracking along the edges, and you can see the chamber comes in to wherever there is less resin, and it releases the fabric to have a higher permeability. And by doing that, you can fill the mold. So now you can also use this to accelerate your flow. And so these kind of things are possible to do. So my dream in general here is to actually have a something like what you saw the advertisement for Moldex 3D for the plastic industry, where you have the simulation that is coupled with the equipment, so that in the end you can get a good part, so that the simulation is actually an integral part of the equipment with the sensors already built in. So so it becomes a turnkey solution. We are not very far from it, but it is within reach now. So we can do that. So this is my final slide. So the takeaways from what I presented today is that we can mitigate costs with the simulation to determine gates and vents to minimize filling time and voids, design process and distribution media for complex geometry, account for variability in process and materials, plan process with passive and active control, integrate part design with the process. So these are some of the things. And now with the AI, you can also take data from the actual manufacturing line and use that with the simulations rather than blindly, to keep improving your process as you go forward. So thank you very much for listening, and I will be happy to answer any questions. I think I actually finished a couple of minutes ahead of time, so we'll have plenty of time for questions. Thank you very much.
One of the questions that came along early on was about the ability to measure the pressure inside of the mold, and other questions related to permeability. So Professor Advani, if you could comment on techniques for measuring pressure and permeability, as those are critical inputs to the entire process.
Yeah, so there have been quite a few studies where you have put in people have put in pressure sensors, such as pressure transducers inside the mold to actually measure the pressure. However, it's not an easy thing because egress is an issue. There was a company called TechScan that actually had made a sensor that would measure pressure at different locations. So you put it inside your mold and then you put the fabric on top of it and it will give you the pressure profile along. And I don't know what happened to that company, but it could do that. We had used it. And now in the recent project that we are working with École Centrale in France is actually using a paper to measure the pressure, but it has to be calibrated beforehand because the way the paper works is it basically has some ink in it, and then the ink breaks at under certain pressure and gives you different colors. And so you have to calibrate it beforehand to do that. But you can't do that during the manufacturing. During the manufacturing, when you're building this mold, you have to put pressure transducers that are flush with your tooling surface and can do this, from one part to the next to give you information about that. Now, once you can measure the pressure, you can get information about the permeability because knowing the pressure and knowing and doing the simulations, knowing what the flow rate you're entering, you can actually back calculate the permeability from that. So you can actually do online measurement of permeability if you're able to measure pressure at various locations and know the flow rate as it's coming in. So.
Thank you. One of the other questions along the lines of permeability was the effect of draping on changing the permeability and whether or not that is accounted for in models, how much it's accounted for in our current modeling approaches, and how accurate that is, how much it's been validated. If you can comment on that whole field of the effect of preforming on the permeability.
I mean, there are models that will take the draping information, which is how the fabrics are changing direction. From that, recalculate the fiber volume fraction, which is a function of the permeability. So if you increase the fiber volume fraction, the permeability goes down there. And then if you change the orientation, the principal direction of the permeability changes. So yes, we have done this. Other people have done this where they have accounted for draping in the flow simulation. And what you tend to find is that it doesn't have like a major effect on it, other than uh, you may be off in terms of how much pressure you need to inject the resin. But as far as the flow fronts are concerned, you see very, not very big change. But it's a lot more work to do that than to just run it by assuming that the permeability is what you had measured when it was outside. But it is possible to do it, and you can, like, our program can take an external program where you have the orientation of the fibers, and then you use a model to find out what the permeability will be in each element, and then you can calculate how the flow takes place in that. So that has been done before.
Another diving more into this with a question around thick parts versus thin parts and some of the challenges when you have to do a fully coupled thermochemical mechanical problem. How much is done there with thicker parts versus thinner parts, and how much have you seen the properties vary through the thickness when you start getting into much thicker parts, and how is that modeled, particularly in light of the fact that as you get into damage initiation, some of those local effects and local properties can become more critical. How do we take that account today, and what might we do in the future for treating those phenomena?
Yeah. So two things. One is that to do the flow analysis in thick parts, it's not you don't have to do anything different. You just have to know the permeability through the thickness. So you have to measure the permeability through the thickness. So you have to know what the permeability is. And then you can simulate the flow in thick parts and see whether you will get any dry spots in different locations or not. When the harder problem is really when you try to couple the problem with non-isothermal flow. So when you have resin that is flowing at different temperature as it goes through the thickness, uh, then you have to actually solve the full 3D temperature solution with convection of the resin, which is a very nonlinear problem. So that is much more difficult to do. And in the end, what you will get from that is what is the temperature distribution through the thickness, which will allow you to calculate the residual stresses and, as you were talking about, address the damage part. The flow part and the isothermal conditions is not difficult at all. It's basically just knowing the permeability through the thickness. And we have done that for like Wartum cases where you have very high permeability of the distribution media, and below that you have this fabric that has very low permeability. So you also found methods of how to kind of handle that.
Thank you. One more question came up on this measurement of permeability. I think it's as much of a clarification, but perhaps others have it as well. So I'll ask the question, and that is, are there direct methods for measuring permeability, or today are we using more of an indirect method where we observe a flow front and then we reproduce that flow front in a model and tune the permeability parameter to reproduce that flow front?
Mm-hmm, mm-hmm. I think we have done both. I mean, there were studies where if you wanted to introduce control, you had sensors in there which will look at, how the simulation said that the flow should reach this node at, let's say, 30 seconds, but it arrived there at 20 seconds. So one can then update the permeability in the simulation and recalculate things. So there are ways to do that, but that it's all of this has been done in the labs, but not much of this has been sort of introduced in the not much has been introduced in actually the production, but it's possible to do it. So once you have sensors inside the mold, you can have this nice feedback system that will allow you to, um, uh, actually get data out during as you saw in our method where we had sensors in the mold. The sensors were telling where the flow front was, and we were able to, address that. So
Thank you. One more here on this whole characterization and input parameters, and that is that if we consider predictive simulations with the dual scale permeability that you were talking about, as well as potentially race tracking, what, in your experience, are the most important input variables to be able to model a realistic case history?
sorry, say again, input variables for doing the dual scale flow.
If you're going to consider dual scale flow and potentially even race tracking, which of those input parameters do you really need to make sure you've nailed down?
Yeah, so usually the race tracking is the most important part. I think, and that's what usually causes the problems. But what we have noticed is you don't need to have an exact value of race tracking. As long as you have a more fuzzy logic type of race tracking, that the race tracking is weak, that means the permeability is about 4 to 5 times higher in the corner region as compared to the bulk region, or race tracking is strong, where it is 10 to 50 times more. The flow front shape doesn't change that much, but it is very, very important to be able to introduce the race tracking if you are going to experience it, because having the right permeability there won't mean much if you have race tracking, because it'll completely change the flow front. And that's what I tried to show today.
Mm-hmm.
So that will be the primary effect. Now, the dual scale is important when you're trying to make parts where you don't want your fiber toes to be unsaturated. And usually, when you make a large part, and you look at it, it looks great. But when you take a cross section and you go and look under the microscope, you will see some dry toes. Now, in some applications, that may not be important, but in aerospace, it is very important. So being able to address the dual scale is important. And for that, what you need to know is your fiber toe permeability in addition to your bulk permeability.
Mm-hmm.
And as I showed in one of my slides, that you can actually measure both of those from one experiment by having the fabric inside the mold, injecting the resin at a constant flow rate, and measuring the pressure at the inlet. You can actually get both the permeabilities of that fabric.
Thank you. Thank you again. Let me transition us, if I can, to a couple of more maybe forward-looking questions. Or
Mm-hmm.
one is one question related to strength and thermal deformation. If you've the how far you've been able to go with limbs connecting it to strength and thermal deformation, particularly in the case where you have a fiber orientation distribution, as in a draped preform. How far have you been able to take this into that realm of predicting thermal deformation and then strength coming from the manufacturing process?
Yeah, I think it's possible to do that, where we have talked about and even tried the system where what you do is, if you solve the non-isothermal problem, so you solve the flow and heat transfer problem until it fills, and at the end of filling, you have the temperature history of each node. It's what the temperature is in each element in each node, or at each node. And then you can transfer that to other programs that already do this, such as Abacus and Compro and other programs that already do the thermal deformation part. So we don't need to reinvent that wheel.
Mm-hmm.
And so the idea is, how do you take the results that we get? Because usually what they do is they start with the initial condition, and because they don't know what the initial condition is, they just assume uniform temperature everywhere.
Mm-hmm.
They solve for the residual stress or other problems, but that is a function of initial distribution of the temperature. So that's why it's important to get that right before you do the other problem.
Absolutely. One is providing the initial condition for the next. Yep. One last question, and kind of a very open question. Someone asked, what other open scientific questions are still out there in this field? What's the science that you'd like to do, say, in the next 5 or 10 years? What are the open science questions?
So I think, as I said, we're still grappling with the fact of permeability, predictions. So how do we predict the permeability accurately in the real situation? So I think that is a pretty hard problem. And we have models out there, but none of them really work that well. So being able to address that, being able to address also what happens at the interface of a porous media and a wall. So right now we kind of smudge that, but being able to use something like a Brinkman solution, where you couple the flow in the porous media with flow along the wall, will give you a better idea about how to model the race tracking. So these are the kind of issues that we'd like to address. I know we are coming to an end, so I'll stop here.
Well, thank you again. Thank you, Professor Advani. Thank you for all those that have asked questions. Thank you to the audience and to our sponsors. And we'll remind you that we can continue to ask questions on the CDM Hub forum, and that we will send a recording of this out to you by email. And we look forward to joining with you again in the new year. Our next speaker will be Professor Connor O'Brady, and then you see those further speakers there. Again, thank you to Professor Advani, and thank you all.